friends, welcome to my channel. Analog circuits. Power supply is an electronic system which converts AC power into DC. A regulated power supply is interconnection of rectifier, filter, regulator. For example, pure AC is given to regulator, pulsating DC filter, fluctuating DC regulator, regulated DC output. AC to DC conversion is required because majority of the electronic system requires DC power. Rectifiers, an electronic circuit which converts pure AC signal into pulsating DC, or which converts a bidirectional waveform into unidirectional waveform. Ripple factor gamma. The amount of AC present in the output of a rectifier is called as ripple. The amount of AC from the signal which contains AC and DC is calculated by the ripple factor. Gamma equal to RMS value of AC component by DC component. Gamma equal to VRMS by VDAC whole square minus 1 under root. VRMS by VDC కి మాత్రమే హోల్ స్క్వేర్ వస్తుంది, పక్కన -1 వస్తుంది అండర్ రూట్. ఫార్మ్ ఫ్యాక్టర్ F equal to RMS value by DC value, VRMS by DC. Gamma equal to root of F square minus 1. F square minus 1 under root. Crest factor C. C equal to peak value by RMS value. Efficiency eta. Eta equal to output DC power by AC input power. Half wave rectifier. Average value of current and voltage. Ideal case IDC equal to IM by pi. IM equal to VM by RL and VDC equal to VM by pi. IDC means average value of current, VDC means average value of voltage, IM means maximum value of current, VM means maximum value of voltage, RL means load resistance. Practical case IDC equal to IM dash by pi, VDC equal to VM dash by pi, IM dash equal to VM whole by RS plus RF plus RL, numerator part VM, denominator part RS plus RF plus RL, VM dash equal to IM dash into RL, where RS means coil resistance, RF means diode forward resistance, RL means load resistance, RMS value of current and voltage. IRMS equal to IM by 2, VRMS equal to VM by 2. Efficiency of half wave rectifier, eta equal to I square DC RL whole by I square DC and RL and numerator, denominator part IRMS square into పెద్ద బ్రాకెట్ వచ్చి ఈ బ్రాకెట్లో అంతా వస్తుంది RS plus RF plus RL that equal to 4 by pi square and పక్కన వచ్చి into RL by RS plus RF plus RL. Ripple factor of half wave rectifier gamma equal to 1.21. Crest factor of half wave rectifier C equal to 2. Form factor of half wave rectifier F equal to 1.58. Efficiency when RS equal to RF equal to 0, ideal case eta equal to 4 by pi square, that equal to 40.6%. Peak inverse voltage for half wave rectifier PIV equal to VM. Transformer utilization factor TEF for half wave rectifier TEF equal to 0.286. Output frequency equal to input frequency for half wave rectifier. Conduction angle for half wave rectifier theta equal to pi for ideal case. Theta equal to pi minus 2 sin inverse V gamma by VM. Pi separate to 2 sin inverse of VA gamma by VM for practical case. V gamma means cut in voltage, VM means maximum voltage, ripple factor FR for half wave rectifier, FR equal to F means input frequency. Full wave center tap rectifier, average value of current and voltage IDC equal to 2IM by pi, ideal case VDC equal to 2VM by pi, ideal case RMS value of current and voltage IRMS equal to IM by root 2, ideal case VRMS equal to VM by root 2, ideal case. For practical case, IM is replaced by IM dash, where IM dash equal to numerator part VM, denominator part RS by 2 plus RF plus RL, and VM dash equal to IM dash into RL. Efficiency, ripple factor gamma equal to 0.48 for full wave rectifier, form factor F equal to 1.11 for full wave rectifier, crest factor C equal to root 2 for full wave rectifier, eta equal to numerator part ఏమంటే 8 into RL by denominator part pi square of RS by 2 plus RF plus RL. Eta is maximum when RS equal to RF equal to 0, ideal case, and eta max equal to 8 by pi square, that equal to 81.2%. Peak inverse voltage ఇవన్నీ full wave rectifier లో వస్తుంది. Peak inverse voltage for full wave rectifier center tap is PIV equal to 2VM. Transformer utilization factor TEF equal to 0.57 for full wave center tap. Full wave bridge rectifier, for full wave bridge rectifier, bridge type, in all the formulas RS by 2 is replaced by RS and RF is replaced by 2RF. For bridge type, PIV equal to VM, TEF equal to 0.812 for bridge type. Conduction angle theta equal to 2 pi in ideal case, theta equal to 2 pi separate minus 4 sin inverse of V gamma by Vm. For center tap, theta equal to 2 pi minus 4 sin inverse of 2 V gamma by Vm. V gamma means cut-in voltage of diode. Remaining parameters are same as full wave center tap rectifier. Remember, type of transformer, VDC, half wave rectifier, normal step down. Type of transformer lo center tap based full wave rectifier center tapped. Type of transformer of bridge center circuit based full wave rectifier, normal step down. Parameter, VDC, half wave rectifier lo Vm by pi, center tap based full wave rectifier lo 2 Vm by pi. VDC value, VDC of bridge circuit based full wave rectifier lo 2 Vm by pi. IDC of half wave rectifier Im by pi equal to VDC by whole by Rs plus Rf plus RL. Center tapped base full wave rectifier of IDC equal to 2 Im by pi equal to VDC by Rs by 2 plus Rf plus RL. IDC of bridge circuit based full wave rectifier 2 Im by pi equal to VDC by Rs plus 2 Rf plus RL. VRMS equal of half wave rectifier Vm by 2. VRM of center tap based rectifier Vm by root 2. VRM of bridge circuit based full wave rectifier Vm by root 2. Ripple factor of half wave rectifier 1.21. Ripple factor of center tap based full wave rectifier 0.48. Ripple factor of bridge circuit full wave rectifier 0.48. Efficiency 80% of half wave rectifier equal to 40.5 into RL percentage by RL plus Rs plus Rf. Efficiency 80% of center tap based rectifier based full wave rectifier equal to 81.2 into RL by RL plus Rs by 2 plus Rf. Efficiency 80% of bridge circuit based full wave rectifier equal to 81.2 into RL by Rs plus 2 Rf plus RL. Peak inverse voltage of half wave rectifier Vm. Peak inverse voltage center tap based full wave rectifier is 2 Vm. Peak inverse voltage of bridge circuit based full wave rectifier is Vm. Regulation percentage Rs equal to half wave rectifier Rs plus Rf by RL into 100. The regulation percentage of center tap based full wave rectifier Rs by 2 plus Rf by RL into 100. Regulation percentage of bridge circuit based full wave rectifier Rs plus 2 Rf by RL, Rs plus 2 Rf in numerator, RL in denominator into 100. TUF percentage equal to half wave rectifier 28.7 into RL by Rs plus RL plus Rf. TUF percentage of center tap based full wave rectifier 69.3 into RL by RL plus Rs by 2 plus Rf. TEF percentage of bridge circuit based full wave rectifier is 81.2 into RL by 2 Rf plus RL plus Rs. Output frequency of half wave rectifier F. Output frequency of central tap based full wave rectifier 2F. Output frequency of bridge circuit based full wave rectifier 2F. Number of diodes of half wave rectifier required is 1. Number of diodes of center tap based full wave rectifier is 2. Number of diodes of bridge circuit based full wave rectifier is 4. Form factor of half wave rectifier is pi by 2. Form factor of center tap based full wave rectifier is 1.11. Form factor of bridge circuit based full wave rectifier is 1.11. Filters. A filter is a frequency of selective network which can be used to pass a desired range of frequencies and eliminate unwanted frequencies. In a power supply, it is used to eliminate unwanted AC components present in the output of a rectifier. Filters are classified as inductor filter, pure AC input, output low LRL. Ripple factor of inductor filter of a full wave rectifier R equal to RL by 3 root 2 into omega naught L. RL and numerator part, 3 root 2 into omega naught L and denominator part. Ripple factor of inductor filter for half wave rectifier R equal to pi RL and numerator part, 2 root 2 omega naught L and denominator part, where omega naught means source frequency, LC filter, pure AC output rectifier ki chesi output lo L pakana C parallel with RL. So ripple factor of LC filter for full wave rectifier R equal to numerator part root 2 XC whole by denominator part 3 XL. XC means reactance of capacitor calculated omega equal to omega naught. XL means reactance of inductor calculated omega equal to omega naught. Critical inductance LC is the value of inductance used in LC filter. at which peak AC free current in the circuit is equal to DC current. LC equal to RL by 3 omega naught. For half wave rectifier, R equal to pi into modulus of XC, the numerator part, denominator part, 2 root 2 XL. LC equal to pi RL by 2 omega naught, where XC and XL are calculated at omega equal to omega naught. Capacitor filter, pure AC input, C are parallel with RL output. For half wave rectifier, ripple factor R equal to 1 by 2 root 3 F naught RLC, 2 root 3 F naught RLC, the denominator part. Peak to peak ripple voltage VR equal to IDC by F naught C. For full wave rectifier, R equal to numerator part 1, denominator part 4 root 3 F naught RLC, VR equal to IDC by 2 F naught C. CLC filter, ఇన్పుట్ ప్యూర్ ఏసీ, అవుట్పుట్లో సికి C1కి C2కి మధ్యలో L వస్తుంది. C2 is parallel with RL. For half wave rectifier and full wave rectifier, ripple factor is R equal to numerator part root 2 XC1 into XC2, denominator part RL into XL, where XC1 and XC2 reactance of capacitors calculated omega equal omega naught for HWR and omega 2 omega naught for full wave rectifier. XL means reactance of inductor. Regulator, electronic circuit which maintains the DC output voltage of a power supply stable or constant in respect of fluctuations in AC supply and variations. There are multiple types. Regulator lo linear, non-linear. Linear lo regulator using discrete component, IC regulators. Regulator using discrete components lo shunt series. IC regulators lo fixed voltage IC regulator, adjustable voltage IC regulator. Fixed voltage IC regulator lo 78xx positive DC output, 79xx negative DC output. Adjustable voltage IC regulator IC 723 lo high voltage request V0 is greater than V, low voltage required V0 is less than or equal to V. Clamper, a circuit which can add DC voltage to an AC waveform. A clamper does not change shape of the waveform, it is only shifts the waveform up or down. Application, a clamper used to reinsert or restore DC component into a waveform which has lost DC component after passing through a processing circuit such as amplifier. Clamper is also called DC reinserter or DC restorer. Clamper means two types: negative clamper, positive clamper. Negative clamper lo add negative DC C diode, positive clamper lo add positive DC C diode. Voltage multiplier, a circuit which inputs in is an AC waveform of peak Vm and output is DC voltage which is an integral multiple of peak AC input V0 equal 2Vm, 3Vm, 4Vm. ఓకేనా. నెక్స్ట్ వోల్టేజ్ డబ్లర్లో ఏం చేస్తామంటే ఫస్ట్ కెపాసిటర్, తర్వాత డయోడ్ యొక్క ముక్కు పైకి వస్తుంది D1, దాని పక్కన C1కి డయోడ్ యొక్క ముక్కు అటువైపు వస్తుంది, దానికి మళ్ళీ ఒక కెపాసిటర్ C0 equal 2Vm, అట్లా లైక్ దట్. BJT characteristics. A transistor is a 3-layer, 3-terminal, 2-junction semiconductor device. It consists of either of 2 n-type and 1 p-type layers of material called NPN transistor or 2 p-type and 1 n-type material called PNP transistor. In transistor, current flows due to both majority as well as minority carriers. That is why it's called a bipolar device. It is current control device. Its input impedance is low and output impedance is high. Thermal stability is less because of leakage current or reverse saturation current. In transistor, all the major currents are diffusion currents. Base currents is recombination current. A transistor represented by 2 diode connected back to back cannot work as a transistor as there is no bonding between base and collector. Current conduction in PNP transistor is carried out by hole, whereas in NPN transistor it is due to electrons. Transistor sections. Emitter, it is heavily doped as compared to other regions. The main function of this region is to supply majority charge carrier, that is either electrons or holes. Base, this section is very slightly doped and very thin as compared to other sections. Its main function is to transfer the majority carriers from emitter to collector. This section is moderately doped and has largest area compared to other two regions because it collects the charge carriers from emitter and base. There is a large amount of heat liberation and so it is powered with large area to dissipate the heat. Common base configuration: IE equal to IB plus IC plus ICB0 or IE equal to IB plus IC. IE means emitter current, IB means base current, IC means collector current, ICB0 means collector to base leakage current. IB equal to 2% of IE, IC equal to 98% of IE. Current amplification factor alpha, where when no signal is applied then the ratio of collector current to emitter current is called as current amplification factor or current gain.
alpha equal to IC by E. Alpha of a transistor is measure of the quality of transistor. Higher is the value of alpha, better is the transistor as IC approaches IE. Collector current can also be expressed as IC equal to alpha IE plus ICB naught. Common emitter configuration. Base current amplification beta. When no signal is applied, then the ratio of collector current to the base current is called beta. Beta equal to IC by IB. Also alpha equal to beta by 1 plus beta. Beta ranges from 20 to 500. This configuration is used when appreciable current gain as well as voltage gain is required. Total collector current IC equal to beta IB plus IC E naught, or IC equal to beta IB plus 1 plus beta into ICB naught, where IC E naught means collector to emitter leakage current. IC E naught equal to 1 plus beta of ICB naught. Common collector configuration CC. Current amplification factor gamma. When no signal is applied, then the ratio of the emitter current to the base current is called gamma of the transistor. Gamma equal to IE by IB. Gamma equal to 1 plus beta, that equal to 1 by 1 minus alpha. Total emitter current IE equal to 1 plus beta IB plus 1 plus beta into ICB naught. This configuration has very high input resistance 750 kilo ohms and very low output resistance. Voltage gain is always less than 1, so never used for amplification purpose. This configuration is used for impedance matching, that is driving a low impedance load from a high impedance source. Characteristics: input resistance of CB configuration is very low, brackets 40 ohms, whereas input resistance of CE configuration is 50 kilo ohms, low. Input resistance of CC configuration is 750 kilo ohms. Output resistance of CB configuration very high, 1 mega ohms. Output resistance of CE configuration is high, 10 kilo ohms. Output resistance of CC configuration low, 50 ohms. Current gain of CB less than unity. Current gain of CE 100. Current gain of CC 100. Voltage gain of CB 150. Voltage gain of CE 500. Voltage gain of CC less than unity. Leakage current of CB very small. Leakage current of CE very large. Leakage current of CC very large. Applications: CB configuration for high frequency applications. CE means for audio frequency applications. CC means impedance matching. Phase shift between input and output is CB means 0, CE means 180, CC means 0. Input and output characteristics of different configurations. The collector current IC is completely determined by the input current IE and VCB voltage. Then the curve between IB and VBE for different values of VC is shown figure. The output characteristics of curve between VC and IC for various output values of IB. DC load lines. DC load line is the locus of all possible operating point at which BJT remains in active region. If base current IB less than IC sat by beta, then the transistor operator in active region. If IB greater than IC sat by beta, then it operates in saturation region. If base current IB less than IC sat by beta, then transistor operates in active region. If IB greater than IC sat by beta, then it operates in saturation region. Maximum value of current IC max equal to VCC by RC, taking VC equal to 0 at saturation. This is the ideal case. Power dissipated in transistor PD equal to IC into VCE. Power dissipation is maximum in active region and minimum in cutoff region and saturation region. Transistor biasing circuits. Bias stabilization. Stabilization is a process of making Q point independent of changes in temperature and changes in transistor parameters. If IC naught, VBE and beta changes simultaneously, then net change in IC delta IC equal to dou IC delta IC naught by dou IC naught plus dou IC delta VBE by dou VBE plus dou IC delta beta by dou beta, where dou IC by dou IC naught equal to S equal to current stability factor, dou IC by VBE equal to S dash equal to voltage stability factor, dou IC by dou beta equal to S beta equal to S double dash application stability factor. Then out of three stability factors, S is most significant reason being if S is within tolerable limit, then other S dash and S double dash are guaranteed to remain within tolerable limit. S ideal equal to 1. Practically S should be less than 20. Alternative evaluation of S equal to numerator part 1 plus beta, denominator part 1 minus half beta into dou I by dou IC. 1 separate minus beta into dou IB by dou IC. Okay na? BJT biasing. Biasing refers to providing appropriate DC voltage and DC current to an electronics devices to operate in desired way. A BJT is biased to operate in BJT in active region so that it can be used as amplifier to maintain IC stable so that the operating point does not drift and thermal runaway does not happen. Commonly used BJT biasing circuits are fixed bias circuits, collector to base bias circuit, self bias circuit. Fixed bias circuit means for బేస్ ఆర్బీ ఇస్తాం, ఫర్ కలెక్టర్ ఆర్సీ ఇస్తాం, రెండు షార్ట్ చేసి వీసీసీకి ఇస్తాం. ఓకే, ఐబీ ఈక్వల్ టు వీసీసీ మైనస్ వీబీఈ బై ఆర్బీ, ఐసీ ఈక్వల్ టు వీసీసీ మైనస్ వీసీఈ బై ఆర్సీ. ఐబీ ఈజ్ కాన్స్టెంట్ ఆర్ ఫిక్స్డ్, hence circuit is called fixed bias circuit. S equal to 1 plus beta, since S is very large, IC will be unstable. కామన్ కలెక్టర్ టు బేస్ సర్క్యూట్. ఇక్కడ ఏమంటే ఐబీ దగ్గర ఆర్బీ పెడతాం, దానిపైన ఆర్సీ పెడతాం, వీసీసీ పెడతాం. ఐసీ ఈక్వల్ టు వీసీసీ మైనస్ వీబీఈ బై ఆర్సీ, అజ్యూమింగ్ బీటా టు బి లార్జ్ ఆర్ ఐబీ ఈక్వల్ 0. ఐసీ ఈక్వల్ టు వీసీసీ మైనస్ వీబీఈ బై ఆర్సీ ఇంటూ బీటా బై 1 plus బీటా. ఎస్ ఈక్వల్ టు 1 plus బీటా అనేది న్యూమరేటర్ పార్ట్, డినామినేటర్ పార్ట్ ఎంత వస్తుంది 1 plus బీటా ఇంటూ 1 separate ప్లస్ బీటా ఆఫ్ ఆర్సీ బై ఆర్బీ ప్లస్ ఆర్సీ. Advantage, it gives more stable IC than fixed bias circuit. Drawback, stability factor depends upon RC. If RC becomes smaller or 0, stability factor becomes very large and IC does not remain stable. Self bias circuit, voltage divided circuit. బేస్ కేమో R1 R2 ఇచ్చేసి పైన R1 కింద R2, రెసిస్టెన్స్ దగ్గర ఇమిటర్ దగ్గర RE ఇచ్చేస్తాం, కట్టర్ దగ్గర RC ఇస్తాం, పైన VCC ఇస్తాం. థెవెనిన్ ఈక్వలెంట్ VTH ఈక్వల్ టు R2 బై R1 ప్లస్ R2 ఇంటూ VCC. RTH ఈక్వల్ టు R1 ప్యారలల్ విత్ R2. IC ఈక్వల్ టు VCC మైనస్ VCE బై RC ప్లస్ RG. IE ఈక్వల్ టు VTH మైనస్ VBE. VTH మైనస్ VBE is న్యూమరేటర్ పార్ట్, డినామినేటర్ పార్ట్ RE ప్లస్ RTH బై బీటా ప్లస్ 1. RE separate to RTH by beta plus 1 separate. So assuming beta to be large, S equal to 1 plus beta by 1 plus of beta into RE by RTH plus RG means 1 plus beta numerator part, denominator part 1 separate plus beta of RE by RTH plus RG. If 1 plus beta into RE greater than or equal to RTH, greater than RTH. Advantages, self bias circuit has the least stability factor among all biasing circuits. Stability factor is independent of RC. Self bias circuit can be used to bias BJT for any configuration. Drawback, resistance RE creates negative feedback due to which voltage gain V0 by Vi or V0 by Vs becomes smaller. Thermal runaway. It is the process of self-destruction or damage of transistor where an increase in temperature increases the collector current, causing further increase in the temperature. Thermal resistance theta equal to Tj minus Ta by Pd, where Tj means junction temperature, collector junction, Ta means ambient temperature in Kelvin, Pd means power dissipation across collector junction. Condition to avoid thermal runaway, a transistor will be thermally stable if dou Pc by dou Tj less than or equal to dou Pd by dou Tj equal to 1 by theta, where dou Pc by dou Tj is equal to rate at which heat is released, dou Pd by dou Tj equal to rate at which heat is dissipated. For thermal stability, Vc less than Vcc by 2. Early effect, it is also known as base width modulation. Due to early effect, common base configuration, common base current gain increases, emitter current increases, punch through or reach through occurs. The output resistance R not equal to numerator part VCE plus VA, denominator part IC. R not equal to VCE plus VA by IC, where VA equal to early voltage. Compensation method. In this method, collector current is made stable by connecting temperature dependent devices such as diode, thermistor resistor or temperature dependent resistors. Thermistor temperature quotient is negative. Thermistor fabricated from pure semiconductor sensitors. Temperature quotient is positive. Sensitors fabricated from heavily doped semiconductors. Diode compensation for IC not. ఇక్కడ పైన ఆర్బీ కింద డయోడ్, ఆర్సీ, విసిసి, ఆర్ఈ దగ్గర గ్రౌండ్, అంటే ఆర్ఈ కాదు ఎమిటర్ దగ్గర గ్రౌండ్. థర్మిస్టర్ కంపన్సేషన్ ఫర్ ఐసీ నాట్. కలెక్టర్కి ఆర్ఈకి మధ్యలో ఆర్టీ పెడతాం. కంపన్సేషన్ ఇన్ సెల్ఫ్ బయాస్ సర్క్యూట్. BJT biasing in integrated circuits. Self bias circuits cannot be used to bias BJT in amplifier because R1 and R2 are large resistances and it requires greater area on silicon chip. Therefore, BJT is biased in IC amplifier using special circuit known as current mirror. Basic current mirror, I out equal to I in by 1 plus 2 by beta. Current mirror is symbolically shown as constant current source. Applications of current mirror. The current mirror is used to bias BJT in IC amplifiers. Current mirror can be used in as active load in IC amplifier. Advantages of current mirror biasing: it requires smaller chip area than self-bias circuit. A current mirror of is equivalent to constant current source, hence the DC collector current of bias transistor remains highly stable. BJT as an amplifier. Common emitter amplifier, output voltage VOT is nearly equal to minus IERC. Voltage gain Vout by Vin equal to minus RC by RE dash. Input impedance Zin equal to R1 parallel with R2 parallel with beta RE dash. Input impedance seen from base Zin base equal to beta IB RE dash whole by IB equal to beta RE dash. Output impedance Zout equal to RC where RE dash equal to 1 by GM equal to VT by IC. Common base amplifier. Input impedance Zin equal to RE dash. Voltage gain A equal to Vout by Vin equal to RC by RE dash. Output impedance Zout equal to RC. Common collector amplifier or emitter follower. DC output voltage Vout equal to Vin minus VBE. Input impedance Zin equal to R1 parallel with R2 parallel with beta RE. Input impedance seen from base Zin base equal to beta of RE plus RE dash equal to beta RE. Output impedance Zout equal to RE dash separate plus numerator part RS parallel with R1 parallel with R2, denominator part beta, that equal to RE dash plus RS parallel with R1 parallel with R2 by beta. Voltage gain A equal to numerator part RE, denominator part RE plus RE dash plus RS parallel with R1 parallel with R2 whole by beta, RS parallel with R1 parallel with R2 by beta is nearly equal to 1. Darlington amplifier. Darlington ఏముంటుందంటే ఓకేనా, ఫస్ట్ ఇన్పుట్ సోర్స్, నెక్స్ట్ ఆర్సీ, నెక్స్ట్ కెపాసిటర్, పైన R1 కింద R2, ఆ మధ్యలో ఒక బేస్కి పోతుంది, కలెక్టర్కి ఏమో VCC పోతుంది, ఈ ఎమిటర్కి ఏమో ఇంకో బేస్ కలెక్ట్ అయి ఉంటుంది, మళ్ళీ దాని యొక్క కలెక్టర్కి ఏమో VCCకి పోతుంది, దాని యొక్క ఎమిటర్ ఏమో RE దగ్గర కెపాసిటర్ పెట్టి Vout తీసుకుంటాం. Impedance of second stage Zin of 2 equal to beta 2 RG. Input impedance of first stage equal to Zin of 1 equal to beta 1 beta 2 RG. AC Thevenin impedance at input RTH equal to RS parallel with R1 parallel with R2. Output impedance of first stage Zout of 1 equal to RG1 dash plus RTH by beta 1. Output impedance of second stage Zout 2 equal to RE2 dash plus numerator part RE1 dash plus RTH by beta 1 whole by beta 2. Input impedance of common collector amplifier is highest among CE, CB and CC. Output impedance of common collector is lowest among CE, CB and CC. Darlington pin is known as a super beta circuit. Darlington pin used for very high current, very high input impedance and high current gain is required. Voltage gain of CB is highest and current gain of CC is highest. CE has highest power gain. Analysis of small signal amplifier. Introduction. In the analysis of small signal amplifier, transistor is replaced with an equivalent circuit known as small signal model. Small signal model means low frequency, high frequency, low frequency, low hybrid parameter model, pi model, T model. These are all used in analysis of BJT amplifiers at medium or low frequency, high frequency, slow, pi model, only T model. HF analysis of BJT amplifier, high frequency, hybrid parameter model. The H parameter model of BJT is defined by two input networks as V1 equal H11 I1 plus H12 V2, I2 equal H21 I1 plus H22 V2. Input impedance H11 where HI equal to H11 equal to V1 by I1 at V2 equal to 0. Current gain H21 or HF equal to H21 equal to I2 by I1 at V2 equal to 0. Reverse voltage current voltage gain H12 equal to V1 by V2 at I1 equal to 0. Output impedance H22 or H0 H22 equal to I2 by V2 or I1 equal to 0. Typical H parameter values of transistor parameters: H11 or HI equal to for CE 1.1K, HI of CC 1.1K, HI of CB 21.6 ohms, HR of CE 2.5 into 10 power minus 4, HR of CC 1, HR of CB 2.9 into 10 power minus 4, HF of CE 50, HF of CC minus 51, HF of CB minus 0.98, H0 equal to 24 microamps of CC, H0 equal CC of 24 microamps per volt, H0 equal CB of 0.49 microamperes per volt. 1 by H0 of CE equal 40 kilo ohms, 1 by H0 of CC equal 40 kilo ohms, 1 by H0 of CB equal 2.04 mega ohms. Approximate conversion of formulas for H parameters: CE to CC. HIC equal HIE CE to CC, HRC equal to 1 minus HRE, CE to CC, HFC equal to minus half 1 plus HFE, CE to CC, H0C equal to HOE, CE to CB, HIB equal to HIE by 1 plus HFE, CE to CB, HRB equal to HIE HOE, numerator part by denominator part 1 plus HFE, separate minus HRE, HFB, CE to CB, HFB equal to minus HFE by 1 plus HFE, HOB, CE to CB, HOB equal to HOE by 1 plus HFE. Hybrid model or low frequency model. Hybrid model or low frequency model. RS H11, H12 V2, H21 I1, H22 V2 RL. Current gain AI equal to minus HF by 1 plus H0 RL and AI dash equal to AI into RS by whole by RI plus RS. Input impedance Zin equal to RS plus HI plus AI HR HL, AI HR RL, RI equal to HI plus AI HR RL. Voltage gain AV equal to RL by RI pakkana RL into AI by RI. Once again AI into RL by RI. AVS equal to V0 by Vin equal to AV whole పెద్ద bracket to RI by RI plus RS. Output admittance Y0 equal to H0 separate minus HR HF by RS plus HI. Under assumption RL tends to infinity and Vin equal to 0. CE amplifier with unbypassed RI equal to HIE plus 1 plus HFE into RE. If bypass capacitor is disconnected, then AV decrease, input and output impedance will increase. Small signal amplifier analysis. Value of large microfarad capacitor. Medium frequency short circuit, low frequency active, high frequency short circuit. Value of small picofarad capacitors. Medium frequency open circuit, low frequency is open circuit, high frequency is active. Capacitors. There are two types of capacitors: large value microfarad capacitors and small value picofarad capacitors. In large value there are CB, CC, CE. Blocking, coupling, bypassed. Small value lo internal capacitance, sectional capacitance or shunt capacitances. Internal capacitance lo junction capacitance of J beta, diffusion capacitance of JE, transition capacitance of JC. Blocking capacitor CB and coupling capacitor CC provide this isolation to biasing circuit so that no DC current flows out of the biasing circuit and no DC current enters the biasing circuit from the outside. Bypass capacitor CE prevents decrease in voltage gain. Capacitor CC FL lower cutoff frequency, CC equal to 1 whole by 2 pi CC into RC plus RL. Bypass capacitor equal to lower cutoff frequency FL means GM by 2 pi CE. Blocking capacitor CB lower cutoff frequency FL equal to 1 whole by 2 pi CB into RS plus RI. Pi model or high frequency model. VB dash equal to VP, V pi, RBB dash equal to ohmic space spreading resistance. CC means collector junction barrier capacitance. E means diffusion capacitance between B dash and E. Typical pi model parameter values for CE transistor. RBB dash means 100 ohms, R0 80 kilo ohms, C mu 3 picofarads, GM 50 milliseconds, R pi 1 kilo ohms, R mu 4 mega ohms, C pi 100 picofarads. Relation between H parameter and parameters of pi model. HI equal to RBB dash plus R pi, G0 equal to 1 by R0 equal to 1 by RCE, HRE equal to R pi by R mu, G mu equal to 1 by R mu equal to 1 by RB dash C, H0 equal to G0 plus 1 plus HFE GU, R pi equal to HFE by GM, GM equal to modulus of IC by VT, RB dash C equal to RB dash E by HRE equal to RP by HRE, RB dash equal to RB equal to HIE minus RB dash E equal to HIE minus R pi. Common enter short circuit current gain AI equal to HFE by root over 1 plus F by F beta whole square. F by F beta మాత్రం వస్తుంది, separate 1. F beta is 3 dB, upper cutoff frequency F beta equal to 1 by 2 pi RB dash E, CE plus CC. 1 in numerator part, denominator part 2 pi RB dash E, CE plus CC. Frequency with which short circuit current gain becomes unity. FT equal to F beta. F beta separate to HFE minus 1 under root, or FT equal to HFE into F beta. FT equal to HFE whole by 2 pi RB dash E into CE plus CC, or FT equal to GM by 2 pi into CE plus CC. Common emitter gain with resistive load at output. AI equal to HFE by root over 1 plus F by FH whole square. F by FH whole square and where FH equal to 1 by 1 numerator per denominator 2 pi RB dash E into CE plus CC into 1 plus GM RL. FT greater than F beta greater than FH. upper cutoff frequency of overall configuration is fh star equal to fh into root over 2 power 1 by n minus 1. fh star for identical amplifiers in cascade, fh star equal to fh 2 power 1 by n minus 1 under root. fh separate, fh root లేదు, where n means number of amplifiers in cascade, fh means upper cutoff frequency of one amplifier. Lower cutoff frequency of overall configuration fl dash equal to fl numerator part by 2 power 1 by n minus 1 under root. fl by root over 2 power n minus 2 power 1 by n minus 1. Approximation baseband of amplifier in cascade is fh star. When amplifier are non-identical, then fl star equal to 1 into root over fl square plus fl2 square plus and so on fln square, and 1 by fh star equal to 1 into root over 1 by fh square plus 1 by fh2 square plus 1 by fh3 square and so on 1 by fhn square. Rise time tr star equal to 1 into 1 of root over t1 square plus t2 square plus and so on tn square. Special multi-stage amplifier. First one Darlington amplifier, second one Cascade amplifier. Darlington amplifier, it is cascade of two common collector amplifiers or cascade of two common drain amplifiers. Darlington, it is cascade of two common collector amplifiers or cascade of two common drain amplifiers. It has unity voltage gain, very high input impedance, low output resistance and high current gain. It is used as buffer. Cascade amplifier, it is cascade of CE and CB amplifiers or cascade of common source and common gate amplifiers. CE and CB means cascade. CE and CB means cascade. It can provide both voltage and current amplification, therefore it is preferred over common base amplifier in radio frequency amplification and wide band amplification. Amplifier using FET and MOSFET. Voltage gain AV equal to V dot by Vi equal to minus mu RD by RD plus 1 plus mu RS minus mu RD in numerator part, denominator part small RD plus capital RD into plus 1 plus mu of RS.